Good evening. I'm here to introduce Richard Gonzalez, who is the Amos Tversky Collegiate Professor of Psychology and Statistics in the College of Literature, Science, and the Arts at the University of Michigan. Rich comes from us originally from California, where he received his undergraduate degree at UCLA, and then his PhD at Stanford University. I've heard of the place. Before taking his first academic position at the University of Washington before coming to the glorious Midwest, where he'd heard the weather was really good. Rich studies decision-making everywhere, both in the lab and in the wild, in medical decision-making and in product design, in eyewitness identification, in transportation. He studies it with biological data and by watching people's behavior. He studies it not only in psychology and statistics, but he's a research professor in integrative systems and design in the College of Engineering, where he co-founded and co-directed the Design Science program. He's a faculty associate at the Center for Computational Medicine and Bioinformatics. He is a faculty associate of the Comprehensive Cancer Center at University of Michigan Medical Center. He's a senior fellow at the Interdisciplinary Michigan Society of Fellows. And for the past 11 years, he has been a research professor and director of the Center for Group Dynamics, the historic Center for Group Dynamics, over at the Institute for Social Research, where he also, because he's not busy enough, co-directs the Biosocial Methods Collaborative. He's received the Outstanding Research Publication Award from the American Educational Research Association. He's received the Jacob Cohen Award for contributions for teaching and mentoring from the American Psychological Association. And the university itself caught up by giving him the Rackham Distinguished Faculty Achievement Award a few years ago. I just summarized 59 pages of Vita. Hopefully I've left 59 minutes more for Rich actually to tell you why there are 59 pages of Vita when he talks about improving the science of decision-making. Rich.
Well, good evening. Thank you for spending your Monday night with me on a beautiful second day after we changed the clocks and it's still sunny. What I'd like to do today is obviously talk about AI, but before we get to AI, I want to talk about the science of decision-making in a historical context so that we can think about the role of AI in decision-making. So what I'm going to put forth is this new idea that I'm calling generative decision-making. So in the same way that we've heard of generative language, generative AI, ChatGPT, and so on, large language models, I'd like to be able to see how we could possibly add the modifier generative to the field of decision-making. So the current status of decision-making is that I think we do a very good job of being able to understand and predict how people will make choices when the choices are known. So if I give you three options and I can specify those three options, we have models that do a reasonable job of predicting which one you will choose. But what we lack is the ability to predict new options that don't exist. So this is the meaning of generative decision-making that I want to get to. So, historical overview of key moments in the field of decision science. And I'll be fairly honest in terms of the positive and negative aspects of this history throughout. I'll talk about some of the challenges to decision-making that I'm sure many of you are already aware of through popular books like Thinking Fast and Slow and Freakonomics and so on. And then talk about where the field is heading. So let's go back to the 17th century, where some of the very early decision-making work appeared in the academic literature. So Pascal was trying to think through a rationale for whether or not we should believe in God. And the way he kind of formulated the problem, and what I want to focus on today is how the problem was formulated. That's the key insight, is he's created what we now call the acts by states representation. But this is a representation where the actions that we can take as a decision maker are the rows of the table. So we can either believe in God or not believe in God. And then there's something that's outside of our control, nature. God exists, God doesn't exist. It rains, it doesn't rain. Those are our things that are outside of our decision-making capabilities. Those are the states. So Pascal sort of said, all right, the states are either God exists or God doesn't exist, and that creates 4 cells in a spreadsheet, so to speak. And let's fill in those cells. Well, if I believe in God and God exists, that's great, I go to heaven, right? If I don't believe in God and God exists, then I go to hell. And so he basically went through, looked at all the possible consequences, and that was the first contribution. He created a way to think about decisions, how to represent a decision problem. He then went further and came up with a decision rule of, well, how do you select an option? And he came up with this idea that we should minimize the worst possible outcome. And so minimizing the worst possible outcome, well, going to hell is the worst possible outcome. We don't want to choose a row that will possibly land us in hell. So we choose the other row that won't get us in hell. Now we call this a mini-max strategy, but basically minimize the worst possible outcome. Let's explore this a little bit, this representation, move away from theology into sort of other types of decision problems. So a coin flip, heads and tails. I have one option that if the coin lands heads, I get $50. If it lands tails, I lose 50. Or a second option where the 2 outcomes are 100 or lose 100 instead of 50, negative 50. If we follow the minimize the worst possible outcome, we would pick A because the worst possible outcome appears in row B, and so we avoid row B because that's the worst outcome, so we would pick A. That's what Pascal would have us think. Now, at this time in the 17th century, there were lots of people, Pascal, Fermat of the famous Fermat theorem, Laplace, lots of people were struggling to figure out how to think about probabilities, how to think about decision-making. And the applied problems that they were struggling with would be, for instance, insurance, right? Shipping industry, you have cargo, you have expensive ships, so there's insurance. How do you price the insurance? How do you figure this out? So, right, there wasn't an actuarial science program that people could get a degree in. This was pre all of that knowledge. So these are the kinds of problems that they were struggling with. They also came up with alternative decision rules. So I gave them minimize the worst possible outcome. Another one would be expected value, which is if you know the probabilities, you can multiply the probabilities times each of the outcomes and then sum the products and get expected value. Well, there's a problem for this particular one because this particular choice, the expected value is 0 in both cases. So expected value won't let you pick A or B because they both have an expected value of 0. So there's no way to pick A over B because you would be indifferent. You could flip another coin to pick A or B. And so the contribution in the 17th century was basically how to think about problems, how to think about actions we take versus other factors that are outside of our control, and then decision rules that we should follow. A lot of thinking about games of chance was happening around that time as well, and communication with letters back and forth about creating new games. And so let's think about this new game. You're offered the following deal. We're going to flip a coin repeatedly until we see the first heads, and as soon as the first head lands, we stop. If heads appears on the first flip, you win $2. If heads appears on the second flip, you win $4. Oh, and the game stops. As soon as the first head occurs, the game stops. If heads appears on the third flip, you get $8, and so on. So you can see the pattern. Every flip, additional flip doubles the prize. So the question that was floating around at the time is, well, how much should we pay to play this game? So if there's an entrance fee, so you're guaranteed to win at least $2, right? Because even if the first flip lands on heads, you're going to get $2. So how much should you be willing to pay? Let's go through some scenarios here. So the probability that the head lands on the first toss is 1/2, and you get $2. Probability of the head landing on the second toss is 1/4, so you get $4, and so on. You'll see a pattern that in the probability column, it's 1/2 to the number of flips, and in the outcome, it's 2 to the number of flips. So in expected value terms, if what we do is multiply the probability times the outcome, when we multiply 1/2 times 2, that's $1. When we multiply, I'm having problems with my cursor, which is why when I multiply 1/4 times $4, we get 1. 1/8 times 8, we get 1, and so on. So if we were to sum this, the expected value is infinity. And so this was a puzzle for these 17th century thinkers, because it doesn't make any sense that you'd be willing to pay any amount of money to play this game because it has an infinite expected value. So something is off, right? Something doesn't quite jive, because most people would not pay more than $20 or $30 to play this game, and many people pay much less than $20 as an entrance fee to play. But you should be willing to pay millions and millions of dollars because the expected value is infinity, right? So something's weird here. Enter Bernoulli. There were lots of Bernoullis. I can't keep them straight as to which Bernoulli. They were all related. Which Bernoulli was, which attached to which scientific contribution. But it was a very accomplished family. Let's leave it at that. And so Daniel Bernoulli came up with the idea of taking the logarithm of the payoff. The specific idea of the logarithm is not so important. The big idea here was the fact that he suggested that we shouldn't necessarily talk about money as money, but we should talk about the subjective value of money. So going from 0 to 1,000 feels like a big jump, but going from 1,000,000 to 1,000,001,000 doesn't feel as big of a jump. So the unit increments are not linear, right? And so any concave function would accomplish what Bernoulli was trying to accomplish. He just settled on the logarithm. The big point is that each additional dollar means less and less to you, what economists now call marginal diminishing sensitivity. And this is kind of the logarithmic curve, right? That it's very curved, it hits an asymptote, so eventually if you're wealthy enough, an extra dollar is so trivial it doesn't mean anything to you. Now, the other detail that I don't sort of want to get into the specifics about, but Bernoulli and many others talked about combining everything over your total wealth. So you don't think about an additional dollar, it's always your wealth plus that extra dollar. And this economists love to do this. So the utility of $2 plus your wealth, right? The utility of $4 plus your wealth, and wealth is always constant here. So when you do this, the expected value, and the expected utility now, because we're using utility instead of the actual outcome of dollars, is less than infinity. And this is kind of one resolution that people were playing with at the time. There were many other resolutions. One that I'll come back to a little bit later was, well, maybe people don't weight probabilities linearly. Maybe the action is not on the dollars, but on the probabilities. Very small probabilities might be ignored. There were other resolutions like, well, if the outcomes get so high, millions and millions of dollars, maybe there's a point at which the payout can't be realistic, right? The house runs out of money. The house doesn't have enough money to pay off the bet that they engaged in. So this is known as the St. Petersburg paradox. The main thing we learn about this is that expected value alone doesn't necessarily help us solve all of our decision-making problems with decision-making under risk and uncertainty. So a couple of centuries later come von Neumann and Morgenstern. What's very important about this, this collaboration is that they actually provided what we now think of as a behavioral foundation for utility. So Bernoulli and other scholars prior to von Neumann and Morgenstern basically asserted utility in the same way that Bernoulli asserted the logarithm for utility. What von Neumann and Morgenstern did, as I'll show you briefly, is they provided a behavioral foundation from which utility is a consequence. Instead of asserting utility to explain behavior, you begin with some behavioral principles. Those principles lead you down the path of proving, actual mathematical proof, that there is a concept of utility and it follows certain axioms. And so utility is derived from rather than asserted. To them, the utility theory was not the purpose that they were trying to address. So they co-authored a book, The Theory of Games and Economic Behavior, which is what today we know as game theory. It's one of the early contributions to develop the field of game theory. And to develop the theory of games, they needed a theory of utility. And so they basically just in passing said, oh, very easy to prove the utility theory, here are some axioms, we leave the proof as an exercise to the reader. It was something like that. Well, this led the field to basically in a tailspin because not very many people were smart as these guys were to figure out what the proof was. And so people begged them to provide the proof, and they finally did in the second edition of the book. The proof is a 25-page appendix. So it wasn't a simple proof at all. The other important thing is that they wrote in the early 40s, is when the collaboration started, a German and a Jew working together on what has become one of the most important contributions in behavioral science. So let's go through the axioms. I'll give you the highlights of what these axioms are. The first one is very simple, it's transitivity. So if option A beats option B and option B beats option C, then it better be the case that A beats C, right? In symbols, it's a preference relation. So if you prefer A to B and you prefer B to C, then you should prefer A to C. Then there's this independence condition, which is basically ordering or preference remains the same if you add the same thing to both options. So if I prefer vacationing in Traverse City to South Haven, then I should prefer Traverse City plus a $100 bonus than South Haven plus a $100 bonus, right? That adding the same thing to both options shouldn't make me change my preferences. I'll talk about some violations of that a little bit. That's the basic idea. In symbols, in terms of probability distributions and so on, if I prefer option A to B, then some mixture, probability mixture, right? Some probability of getting A with some probability of getting C should be preferred to the mixture of B and C. So this idea of adding the same thing to both sides is operationalized as a mixture. There's some technical axioms too that I don't need to get into too much details about, but there's a completeness axiom which basically says for any two options, something's got to give. Either you prefer A to B, or you prefer B to A, or they're both you're indifferent to both. You can't throw up your hands and say, it's impossible to choose. That's one of the axioms. And then there's a continuity condition, which basically allows you to map everything to the real numbers. Another historical point about this representation and kind of why this was such a big deal is that, there's a period in the social sciences from about 1910 all the way up into the 50s and 60s where the field of social science, broadly defined, was very concerned with making sure that everything we do is based on observations. So logical positivist movement in philosophy, if you're familiar with that. We don't want to have any vagueness in our theories, right? Everything should be operationalized and measurable, and this is the context in which these axioms and this work that von Neumann and Morgenstern contributed occurred in. So they basically provided a way to measure concepts in the social sciences. So anything that involves measurement is a mapping from some set of objects to the numbers. And the object should have the same properties the numbers do, otherwise we can't do the mapping, right? So numbers are transitive. 5 is greater than 4, and 4 is greater than 3, and 5 is greater than 3. So if I want to map something onto numbers, the thing I'm mapping better have that property, because otherwise the mapping doesn't exist. So that's the reason why these axioms were kind of set up the way that they did, is to basically provide a foundation for measurement. And in a way that the physical sciences has the benefit where they don't have to worry so much about these issues. In the social sciences, where the concepts are a little bit fuzzier, we have to worry about the foundations of how we measure things. So you put all of these axioms together, and what you get is a theorem, an actual mathematical theorem that says there's a preference relation, which is this squiggly greater than with a squiggly underneath it, greater than or equal to, but it's not the usual greater than or equal to, because that's reserved for the numbers. Numbers can be greater than or equal to. So that's the right-hand side, right? On the left-hand side, we have the squiggly one. And so the whole point of this exercise is to show that you can go from fuzzy left side that has certain properties to the quantitative right side that also has properties, and back and forth. It's an if and only if. So if the numbers go back to the properties and the properties go to the numbers. The other interesting thing about this is that the idea of a long-run average, which is what Bernoulli and Pascal and Laplace all argued for, why you used expected value or expected utility, you don't have to assume long-run average. The long-run average is a consequence of assuming transitivity, completeness, independence, and a continuity condition. You have to assume continuity because the numbers are continuous. And so again, that same idea. If the numbers are continuous, then the domain in which you're measuring should also have that property. This idea of how we measure things was very popular from about the 40s all the way up until about the 80s or 90s. And then unfortunately, it just has died off. The social sciences don't seem to do this as often, and it's not as a high priority as it was during that 50-year period. The University of Michigan was foundational at developing this approach, as some of the names will come up in the rest of the talk. All right, let's go 10 years ahead. So 44, now we're about 52, 54. Maurice Allais, French economist, very interested in what's happening with von Neumann and Morgenstern and these axioms and expected utility theory. And he gets this idea to do a survey where he asks a bunch of questions, like, do you prefer A to B, and do you, C to B, or C to D, and so on. But the participants are economists, academic economists, the theorists. So how does he do this? Well, there's a conference in 1952 in Paris where a lot of these people that I'll be talking about attended the conference, and he distributed a little questionnaire with choices during the break. And then prior to that conference, he also sent correspondence out to a bunch of other economists that he knew would not be at the conference, just to get their responses as well. So what's an example of one of the questions that he gave them? Well, a choice between getting $1 million for sure, or this complicated chance. 10% chance for 5 million, 89% chance for 1 million, or 1% chance is 0. You could maybe walk away with nothing. The most common response that Allais observed among the economists who responded to this survey was A. They take the 100 for sure, the 1 million for sure, forget the gamble, that small 10% chance at 5 million. They got $1 million, they walk away, with a lot of money in their pocket. All right, then there's a bunch of other choices, one like this one. All right, now C and D, brand new choice, 11% chance for 1 million, 89% chance for 0, or 10% chance for 5 million, 90% chance for 0. Now, the reasoning that a lot of the economists followed is this. They chose D because they would say, well, the difference between 11% and 10% is so tiny. It's only 1%. But we're talking 1 million versus 5 million. So, of course, you go with D because D has a much higher outcome for almost the same probability, like 10%, 11%, who cares? The problem is that if you pick A and D together, you violate expected utility theory. And so this is the beauty of the Allais' work, is that the very people that were proposing expected utility theory and proving theorems and arguing about the axioms and stuff were violating their own theory in terms of the decisions that they were making. Right? So the inconsistency is not picking A or B by itself. Expected utility theory doesn't have anything to say about just the A-B choice by itself. It doesn't have anything to say about the C-D choice by itself. But to be consistent, if you pick A, you've got to pick C, or if you pick B, you've got to pick D. And I'll show you why in a minute. But before I give you the answers to why, I want to sort of explain what happened when Allais presented the results. Because at the same conference, he was one of the speakers towards the end, and he basically said, well, here are the data I collected during the break, and you violate your own theory. Well, some economists just didn't care, right? But one of them, Leonard Savage, unfortunately it got blocked off as Savage, S-A-V-A-G-E, who spent time at the faculty here at the University of Michigan in statistics. He was very bothered by this in terms of his own behavior. He was struggling, like, well, is the theory wrong? Did I make a mistake? Did I not understand the problem? What happened? Well, he struggled with this so much that 2 years later he wrote a book called The Foundations of Statistics, which is basically him struggling through his own responses to violating the theory that he was proposing, that he developed an extension of the theory and a very simple way to show that picking A and D violate expected utility theory. So let's go back to the acts by states matrix that we talked about earlier. And so in red, I highlight that both option A and B give you $1 million for the states. So let me explain the states. So imagine that we have a box with 100 pieces of paper numbered 1 through 100. And you're gonna draw a piece of paper. So if you draw any number between 1 and 89, you get $1 million. If you draw, between 90 to 99, you get 5 million. I'm looking at B now. And if you draw the number 100, you get 0. Well, that corresponds to the Allais of the 89% chance for 1 million, 10% chance for 5 million, 1% chance for 0. And 1 million for sure is, regardless of what ticket you draw, you're going to get $1 million. So it's a ones across. The second pair, CD, is exactly the same structure, except in red, instead of both being 1 million, they're both 0. So remember, the idea of independence is you add the same thing to both sides. So if I picked D over C, now I'm going to add 1 million to both sides. I should pick B over A. I shouldn't switch my preference to A if I pick D. And it was this representation. He kind of, Savage went back to basics and said, let's structure the problem the way the field has defined the way we should think about decisions. And now the paradox that LA came up becomes clear that I, as a decision maker, this is Savage speaking, made a mistake. A different attendee at the conference was Paul Samuelson, who basically is credited with bringing calculus to economics. So if you ever sat through an economics course, we were taking derivatives and so on, it's all because of Paul Samuelson. He said, I'll satisfy my preferences, let the axioms satisfy themselves. So for about another 20 years or so, the field was struggling. All right, there's a problem. Expected utility theory seems to be violated in very natural decisions. We could either go with Savage and say, no, we made a mistake, and these are the decisions that we should follow expected utility theory, or we should rethink the underlying theory. Now come Danny Kahneman and Amos Tversky. The girl in the picture is the daughter of one of their collaborators. And Amos was a graduate student here at the University of Michigan. He got his PhD in 64, 65. And Danny Kahneman was a visiting faculty member in the late 60s, early 70s. You've probably heard about prospect theory if you've read Thinking Fast and Slow. Danny Kahneman, Kahneman got the Nobel Prize. Tversky would have been in there too, but unfortunately he passed away before the prize was given, and you have to be alive to get the Nobel Prize. I think of prospect theory as not really having a new novel contribution. Their contribution was to synthesize everything that was known up until that time. So they took Allais-style violations, not just the ones that Allais showed, but many, many others, and were able to sort of organize them in some nice structured way. They took this idea that maybe we don't talk about total wealth, but rather we think about changes from our status quo, gains and losses. Remember Bernoulli with the idea of thinking about adding to wealth. Kahneman and Tversky said, maybe that's not exactly right. But they weren't the first ones to say that. And Friedman and Savage, the same Savage that struggled with his responses to the Allais question, had a paper that basically with Friedman, the famous Milton Friedman, the economist, where they argued that maybe we shouldn't be talking about wealth, we should be talking about gains and losses. And Markowitz also had a paper in '51 making the same point. Kahneman and Tversky also talked about the probability side, and that maybe we don't necessarily think of probability in a linear way, like 0.5 isn't 0.5, in the same way that a dollar isn't a dollar. So they took the idea of moving from dollars to utility and did the analogous operation from probability to decision weights. That also was not new. There are many, many papers. Ward Edwards, who was a faculty member here at Michigan, Tversky took classes from Edwards, took, knew Savage when Savage was here. And then there's one more. And the original paper of prospect theory, they didn't include subjective probability, but then later they added the growing field of subjective probability. So prospect theory really synthesized much critique and disarray in the field of decision making. And it wasn't until they came along that everything kind of got organized under one nice umbrella. So let me go a little bit more into what their contributions were. The gain and loss idea is very important. Let me show you this example that came from them, same outcome but a different feeling. In one case, you were expecting to get a $500 holiday bonus, but you only got $200. So this feels like a loss, right? You're out $300. Or you were expecting nothing. You didn't, you thought that this year there would be no holiday bonus. And surprise, you get $200. Well, both of those situations are identical in that you have $200 in your pocket that you didn't have the day before. But one feels good and the other feels bad, right? One feels like a loss. You didn't get the $300 you were hoping for. And the other one feels like, wow, you got $200 that you weren't expecting. But in both cases, you have $200. They're identical with respect to the final total wealth, your final asset position. But the path you got there is what's key. Okay. Today, we see things like, when you go buy something at a store, there could be a cash discount, or you pay by cash, there's a discount, or there could be a credit card surcharge. This is the cash price, but if you pay by credit card, there's an extra fee. Right? This is the same idea. You're paying the same amount in both cases. It's how it's framed, a credit card surcharge or a cash discount. And this idea of framing was a contribution of Kahneman and Tversky, but again, synthesizing knowledge that was already there. The ideas that I just talked about with respect to sensitivity are described in this value function that now has an origin. So the traditional utility theory has no origin because everything is added or subtracted to wealth. And so now there are changes from a status quo, an origin. Either you gain something or you lose something. And there's the standard idea of diminishing sensitivity, that an extra dollar feels less to you. So going from 0 to 100 is bigger than going from 900 to 1,000. And then the analogous sensitivity, diminishing sensitivity on the side of the losses. There's this reference dependence that we don't like just put everything on wealth, but we think about gains and changes from our status quo. And then an idea called loss aversion, which is the loss side is steeper than the gain side, so it's not symmetric. So you put all these together and you get the value function that's on the right side with one possible functional form, which is the power, but there are other, the power is not the important thing. Then on the probability side, they proposed this weighting function, which is how we transform probabilities into weights. And the first idea is that we overweight small probabilities. Okay. This might be one reason why we buy lottery tickets. So we know winning in the lottery has a very small chance, but if we overweight small probabilities, we could use this intuition to help us understand behavior in lotteries. We underweight large probabilities. And the diminishing sensitivity that we saw in the value function for outcomes also appears on the probability. So moving away from certainty or impossibility. In other words, moving away from 0 or 1, we become less and less sensitive. So it's concave on the left, convex on the right. And here's one possible functional form that has been used in the literature. The other thing Kahneman and Tversky helped organize was this, what they call the fourfold pattern. The popular literature media has picked up on half of the story, not the fourfold pattern, but the two that I'm presenting here. So you probably heard the phrase, people are risk averse in gains and risk seeking in losses. Well, that's only true when the probabilities are high, because the probabilities are underweighted. And that is true, they did say that, but they also said the reverse for low probabilities. So for low probabilities, we're risk-seeking, right? We buy lottery tickets. And for low probabilities in the domain of losses, we're risk-averse. So their original paper had the fourfold pattern, but somehow the popular literature has only picked up on half of it, the half that only applies to the high probability case. I want to focus a little bit on the probability to motivate the connection to AI in a little bit. I'm going to skip this, and I'm going to go right to this, this representation. So imagine that there's a series of choices that you're faced with, and at the top is the base pair between a gamble that has 5% chance for 240 or 7% chance for 200. And I'm going to create additional choices by adding some chance of winning 200 to both sides. So I'm doing that sort of a lay style, add the same thing to both sides to see if choices change. So this ladder, as I move down the rungs of this ladder, expected utility theory would say the choice probability should remain the same. So if the probability transformation that I showed earlier, where people overweight small and underweight high, that concave convex pattern, under that case, as I move down the rungs of the ladder, I should expect to see an increasing percentage of people choosing the risky up until the inflection point, and then there should be a decreasing curve. So the data this is an example of the data. As I move from left to right, I go up, the rungs of the ladder from rung 1 to 2 to 3 to 4, the probability increases of people choosing the risky, people choosing the option on the left. And then when I hit that inflection point, the probability goes down. So the risky looks less and less attractive as I add the same thing to both sides, and that gets larger and larger. The representation of this this ladder is helpful to think about all possible lotteries that one could create for a fixed XYZ, where XYZ are the outcomes. So in the outcomes in the ladder was 240, 200, and 0. So if I keep that fixed and I think about all the possible probabilities that I could give on that, I could give you 240 for sure. That would be probability 1, 240. Or 0 for sure. You know, nothing happens. That's probability 1 for 0. And then all the possible distributions over XYZ. That will form a triangle, a probability simplex, that represents a point in that triangle is an example of one option. Okay. The base pair, the 7% chance for 200 or 5% chance for 240, are the two dots. Adding the rungs of the ladder are basically these little line segments. Each rung in the ladder is just a different line segment. So think of these as probes, and if I could find a way to estimate choice probabilities, the probes can tell me the direction of choices as I move from left to right. And much like you can infer a magnetic field by looking at how the iron filings line up under a magnet, we can infer a utility function by how choices align themselves around these probes. Okay? So here I have a contour plot where the contours represent equal options. So this is the contour curve for expected utility theory. And the thing about expected utility theory is that the contour curves are straight lines and they're parallel. The slope doesn't matter. The slope is just tied to the slope of the utility function. But what matters is expected utility theory predicts straight lines that are parallel. The parallel, it comes about because we assume transitivity. If transitivity doesn't hold, then the lines will cross and the curves aren't parallel. Prospect theory has indifference curves that are a little bit curvy, but there are regions where they're pretty straight. Right? So I'll go back and forth between expected utility, prospect theory, expected utility, prospect theory. Where prospect theory has straight lines, prospect theory makes the same predictions as utility theory, expected utility. It's only in the regions where you see curvature that prospect theory makes a different prediction from expected utility theory. And this was Allay's insight, is that Allay went right to the region where there was the most curvature, where there's the maximal separation from expected utility theory. If you just started creating gambles at will and sort of created lotteries and gave them to people, the majority of that space has straight parallel lines. So you're going to find support for expected utility theory. You kind of have to understand the structure of the game and people's preferences to know where the critical tests of the theory are. Here I have a three-dimensional representation of that contour curve. So what I showed you, the bottom, the floor of that are the contours. Oh, it's not turning. It's turning for me, but it's not showing up there. Oh, I think I have to go here. There we go. So the contours are the bottom triangle, right, that we saw. The utility surface, if we were to project the surface, we create the contour curves on the bottom. But the surface is what we're trying to model, what we're trying to sort of see that magnetic field that we observe from the probes that we put in. There we go. So my collaborator, George Wu, who's at the University of Chicago, and I did quite a bit of work where we went through and created probes that go left to right. We created probes that go up and down vertically, and we created probes that go diagonally through the triangle, so we can infer that whole curvature of that three-dimensional structure that we talked about earlier. And what we found in the meta-analysis from not just our work, but through much of the published literature, is that the triangle can be broken down into three regions where you have a particular pattern in how those slopes are changing, which are consistent with this probability weighting function that Kahneman and Tversky proposed, where there's overweighting of small and underweighting of high probabilities. We developed a machine learning algorithm to basically reduce the number of queries. So with just a minimal number of queries, we can bring a person into the lab and ask them a series of questions and be able to estimate this curve that they have. And I'll skip this and talk about the gamble. So when I give these talks, people ask me a lot about, well, it doesn't sound very exciting. All the work you've done, you've only talked about probabilities and outcomes, and decisions are a lot more than that, right? Decisions have emotions and gut level feelings, and so none of that was in here. And yes, absolutely, the field completely agrees with that critique. For us, a gamble is an abstraction that plays the role of the fruit fly to a geneticist or the vacuum to a physicist. We know that let's say a physicist, there's friction in the real world. Well, you assume friction away. In a vacuum, there's no friction, and then you can test your laws. Then when you go apply it in the real world, you have to deal with friction, right? Well, for us, the gamble is that simple abstraction The theories are only about the consequences, what happens if you, right, if a combination of what you chose and the state of nature come together, what happens. There's probabilities involved, so outcomes and probabilities, and then how you combine them. Do you use a minimize the worst possible outcome? Do you use expected value, expected utility, prospect theory? How do you combine that? So the theories are not about these other things like friction, but that's the limitation of where we are right now. We need to bring those other concepts into our theorizing. There's quite a bit of attention right now on data-driven approaches, large-scale machine learning algorithms where we throw hundreds and thousands of studies, of data sets into the algorithm, tens of thousands of choices, large data sets with large samples across many countries. And consistently what these algorithms find is either expected utility or prospect theory. So the top row is expected utility. We have some value function and then linear probability. Or the bottom row is the value function that I presented earlier, and then the weighting function of small probabilities are overweighted, large probabilities are underweighted. Another critique that we get is, well, there's more to decisions than just what you presented, that acts by states. Some decisions don't follow that. So for example, when Goldilocks goes into the cabin, right, that the bear's left open, and she tastes the porridge. Well, one's too hot, one's too cold, one's just right. She's not computing expected value on that. She's actually evaluating each option compared to some ideal that she has. And she's trying to find the one that's closest to the ideal. So that's more of a distance representation. How far is this from what I want? And the models I presented so far don't capture that psychology. Well, faculty member at the University of Michigan, Clyde Coombs, who was Amos Tversky's dissertation advisor, came up with a model that covers this ideal point, this idea, this notion that we have an ideal in our head of what we would like to have, and when we go shopping, we're constantly searching for what is closest to that ideal. Why don't economists talk about this? Well, in most economics textbooks, this model is dismissed right away. So in an early chapter in this microeconomics textbook by Hal Varian, who was a Michigan faculty member at one point, he's now at Google. He has this idea, this figure that says there's a bliss point or saturation point, and indifference curves kind of all hone in on that, and we would, economically, you'd want to go to that ideal point. But he dismisses that and says the choices that people actually care about are choices of this sort, and so they're not, we're going to dismiss that whole model for the rest of the book. Because the logic is, why would you own more of something that you don't want? Or why would you own more of something you want, but more than you need? And so they basically dismiss this model, this notion of an ideal point. So the last few years, I've been running with this ideal point model because I think it's for a whole set of consumer goods, this is the perfect model. If you've ever gone to go buy a pair of running shoes or walking shoes, and you try them on, and some have too much cushion, some have not enough cushion, some are too firm, some are, right? We're Goldilocks. We have some notion of what we think the perfect pair of running or walking shoe is for us, and we try on different pairs until we find one that matches what we want, that ideal point. So I've extended Clyde Coombs' model into more of a decision-making model where I can take a representation of choices. So here's a case where we actually had people run in shoes. I skipped over the slide, but that's fine. People ran in 5 different shoes. They brought their normal running shoe that they use habitually. And then we had 4 additional shoes in the lab that spanned the market. There were some minimal shoes and stability shoes and super shoes and so on. So participants ran on a treadmill. We got rank orders of they like this one the best, this one the second best. And from there, we were able to create these cubes where there are dimensions that represent their preferences. But the cool thing about these cubes is, so here we have in black are the 5 shoes, and then red are the ideal points. You'll see that there are people have ideal points where there is no shoe. This creates an opportunity to develop new shoes that might be where people want. Using some machine learning algorithms, we were able to map on different characteristics of their running form to the dimensions in the cube. So an important part of your running form is how much, whether you're a bouncy runner. The technical term is center of mass oscillation. But basically, are you a bouncy runner or are you less bouncy? It turns out that the center of mass oscillation was very predictive of one of the dimensions in that cube. And then the other dimensions were predicted by the Shank variability. So basically your step length essentially is what that was. And then the step rate variability, the number of steps per minute, but the variability of that, not the actual number of steps, somewhat analogous to heart rate variability versus heart rate. So in principle, I could bring a runner in, have them run on a treadmill with the proper instruments, get these metrics, and be able to plop them as an ideal point in the cube, and now I can predict their preferences for their shoes. And I can do that for a new shoe that doesn't exist. So in green, there's shoe E there. And if I can map on shoe characteristics to that dimension, to the dimensional space, now I can basically give an engineer the metrics by which they have to create a new shoe, right? So we did that as well with a different type of machine learning algorithm. Here we had 22 shoe metrics. So these examples would be the weight of the shoe, the heel lift, the amount of cushion in the forefoot versus the rear foot, cushion, different stiffness metrics and torsion metrics. And we were able to map that on to the dimensions. So now I can both take a new runner, identify them in the space, be able to see what their ideal shoe is, and be able to work backwards and produce the shoe that corresponds to the ideal point. Or find a close match, find a shoe that exists in the market that's closest to that ideal. Let's skip that. I want to talk about romantic relationships in this context, mainly because there's a connection that you'll see in a minute. Ideal point models can also be used in the context of relationships, including romantic relationships. So I can have an ideal partner, and I can evaluate my current partner to that ideal. It turns out that that evaluation is highly predictive of satisfaction in a relationship. So if your current partner is not close to your ideal partner, you're not satisfied. But that doesn't predict commitment. Commitment is a different operation. If I compare my current partner to the available partners that are out there in the marketplace, if you want to use that metaphor, then that comparison is what drives commitment. So if there are people out there that are much better than my current partner, I'm less committed. But if the people that are out there are equal to my current partner or not as good, then I'm more committed. Now this sounds like a crazy kind of way to think about relationships, but actually Hal Kelly and John Thibault proposed quite a large body of work that has this as one of their foundations. And Hal Kelly did a postdoc here at the University of Michigan at the Research Center for Group Dynamics. This is an extension of this ideal point model, right? That again, it's not expected value, it's not the economic way of thinking, but it feels very natural for us to be comparing what we're experiencing to some ideal that we have. And a decision rule is how close or how far apart the option is to what we have. So I want to come back to this slide, right? The idea that now we have a way, a proof of concept, to be able to create new decision options, like the shoe example that I gave earlier. It arises because we had to break away from the shackles of that thinking, that decision that our field has given us. On the other hand, I want to talk about that shackling process because I think this is where AI is both good and bad. So on the side, I've been playing with this counterfactual of what if famous scientists in history had access to data science or AI? What would they have done? Would they have been able to reach their discoveries much faster? And so I've been playing with data that they had available. So if you know the story of Kepler discovering the elliptical orbits of the planets, he used some data collected by Tycho Brahe in an observatory in Copenhagen. And Tycho Brahe's purpose in life was to basically collect clean, rigorous, robust data so that people can test theory and understand the movements of the planets. And so his observatory was like the classic model for how one collects data at that time. This was in the late 1500s. Kepler wanted to study the motions of planets, and so he used the data that Brahe had collected. And the contribution that Kepler made using principles from physics was that the planets follow an elliptical orbit around the sun. Right? You probably learned all this in high school. What did the data look like that Kepler was looking at? Well, the data were quite sparse by today's standards. What was the data on Mars, let's say? Well, the angle of declination, which is basically from the night sky, the angle that Mars appears, and not left or right, no, just kind of what's the angle? So is Mars way up high or is Mars by the horizon? Just that angle. And so on the right are the data for different days that were being observed over many, many years. There's holes there because their data weren't collected or the concentration was on another planet or another object in the sky. So those are the data. It's actually very easy to train a neural network to model these data and to predict where Mars will appear today in the night sky at that observatory in Copenhagen. So I did that as a little exercise, and I can predict perfectly where Mars will appear in the night sky in Copenhagen. But there's a problem with the data. And it's not a problem that the data is telling us something wrong, is that if you just looked at the data without understanding the problem, you would completely miss, which Kepler did not miss. So if you were to follow Mars along the night sky over many, many days, let's say it's, I can't tell whether it's moving left or right. It's moving from right to left. So you see at the far, far right, it's kind of over many, many nights, it's moving towards the left, but then all of a sudden it does this little curlicue. And then it goes back, right? It starts to move back to the right, and then it goes back and starts moving to the left and continues. So that little curlicue is in the data right here. There's like a little kind of back and forth there, and up there it's kind of hard to see. But that's in the data, right? The data actually have that, what Mars looks to be kind of going backwards and then continuing in the direction that it was going towards. But this is an optical illusion. That's not the way Mars actually travels. What's happening is that because the position of the Earth and Mars and the background of the night sky are in different positions, and Earth and Mars are moving in different speeds, there are times in which, I'll have to step away from the mic to show you the point here, but you'll see that if you're here, you go to there, you go to there, projecting Mars on the background of the night sky, as Earth starts moving faster than Mars, all of a sudden there's a change and it looks like it's moving backwards and then back in the other direction. So if you looked at the evidence, you would try to model that. And that's what the scientists before Kepler did. They came up with really complicated theories, epicycles and all these kinds of crazy things to capture what was in the data. But what's in the data is an artifact of our observation system. And Kepler was able to break away from that and say, no, Mars is actually following an elliptical orbit, and we need to drop that information from the data. So if we want to apply AI, we need to make sure that we're understanding the problem correctly and that AI is approaching the problem correctly. Because the neural network that I developed to predict where Mars is going to be in the night sky today doesn't give me this understanding. It doesn't tell me that Mars follows an elliptical orbit. All that it does is it predicts where Mars is going to be. It correctly gets that little curlicue pathway. So now if we were to apply this to any other data set that we have, right, we would make correct predictions, but we wouldn't necessarily have the knowledge that, for instance, Kepler contributed. And so while I'm very excited about the possibility that AI has in helping us understand decision-making, this idea of generative decision-making and being able to produce new running shoes to match people's ideal points, I'm also very concerned that we don't lose sight of what we do as scientists, what we do well, which is provide a fundamental understanding of how things work. And for science, prediction is not the end goal. Prediction is the way we test our understanding. So if we understand something, we make novel predictions and we can go out and test them. And if they don't play out, then we know something was wrong in our understanding. But it's that interplay between understanding and prediction that is the value science brings to the table. So I'll end with that and hope that we can get to this place where we do generative decision-making in a way that actually helps us understand how people make decisions so that we can help people make better decisions.
And with that, we'd like to open the floor to questions. We ask that you please reserve your question until the microphone arrives to you to ensure that your question is relayed to both the recording as well as the live stream so that they can hear you.
So I understand most of what you're saying, but it doesn't sound like it still takes into account how humans think or don't think. So you said there was something about perfection or the ideal, and you don't need more of what's perfect or something. I forgot exactly how it was worded. But in my mind, 1 cat is great, 2 is ideal, but 6 is also great. So sometimes having more than you need or more than you wanted is still fantastic. So how are you going to model that in? Put that in the model.
Right. Well, that the economists have trouble with that, right? Because there's a point at which too many doesn't work. But from our ideal model perspective, that can work as well. And the kind of classic example is drinking tea, and how many teaspoons of sugar you want in your tea. And some people don't like, they don't like any sugar, so there's 0 teaspoons. And some people like 1 or 2 or 3, and some people like it super, super sweet. They can just put the whole ton of sugar in there. And so this ideal point model can handle all of the extreme from one to the other, whereas a traditional decision-making model could have trouble accounting for those kinds of things. So to me, the distinction between I hope you picked up on an abrupt change in the talk where I was talking about decision rules, like expected value, expected utility decision. And that was a very constrained way of thinking in that acts by states representation. You have to pick a row and you have to have a rule to pick a row. And then boom, all of a sudden it's Goldilocks. And it's not that at all. It's I'm making evaluations at a very different level, and it's not probabilities. It's a very different animal completely, and the field has been focused so narrowly on that original representation, like the fruit fly, right? Genetics based on fruit fly, decision making is based on the gamble, probabilities and outcomes and decision rules, and we miss the opportunity to basically connect to a broader set of decision problems for which other things might be easier, like being able to do this generative AI where we can create new running shoes for people. So. But then at the same time, not having a representation can lead to problems like the planetary or problems that we could be seeing data and trying to model data without completely understanding how those data came to be. So that I haven't figured out that tension completely. I want representation, but I don't want representation.
I'm not sure if this is going to make sense or not, but so we have the Goldilocks moment, where we have enough. So are people trying to figure out an algorithm to move you off of that Goldilocks moment to be, when you compare it to our society and the drive for more? Is that calculated in there of how do you move that needle from satisfaction to I want more?
Right.
Does that make sense?
Right. You want more, or you want something else. So, one way to think about marketing is that it's designed to move you from where you currently are to some other location in the space. So now that you have a new ideal and then you buy the product that they're trying to sell you. And sometimes it might be easier to move the ideal point than it is to convince you to remain at your current ideal point and actually look at this option that they're trying to sell you. It might be easier just to move your ideal point somewhere else. And ways of doing that could be by influencing you through social media, your friends, using influencers, celebrities, people that you maybe could easily move a little bit in the direction that they represent, your ideal point. So it's a different way of thinking about marketing, which is not this traditional representation. So the acts by states matrix, you probably saw similar matrices in things like Consumer Reports, where if you're looking to buy a refrigerator or camera or new TV or cars, the rows are the goods, the objects that you're buying, and the columns, they're not states of nature, but rather they're the attributes like the price, the reliability, the features that the product might have. And then Consumer Reports does some calculation where they look at all the rows and they compute some expected utility-like thing, and they have a best buy or recommended. And it's not, they don't just go with price alone, or they don't only go with reliability. They're doing some compensatory where you pay a little bit more, but you gain a lot more in reliability, right? So they're allowing things to trade off. That's a very traditional way to think about how we make decisions in marketing and how to nudge people. I need to convince you that actually reliability is an important factor, and you should really look at reliability because actually I have the most reliable. That might not be as easy as sort of getting you to think about your ideal point and nudging your ideal point over. Now I don't have to talk about reliability and price and all the factors. I just have to move the point over.
So I just wanted to clarify. So you talked first about the utility, right? Functions. Then you talked about the ideal, kind of moving to the ideal. It felt to me, based on your presentation, like those two are solving kind of different problems. Are there some problems like that can be solved by both, or like approached by both theories?
Right, yeah, it's hard to think about what your ideal gamble is, and you could easily argue that your ideal gamble would be 100% chance for the highest amount of money. Right? You get the highest amount of money for sure. So yeah, I moved away from problems of risk and uncertainty because the ideal point model has a little bit harder time kind of thinking about risk and uncertainty to different kinds of problems that don't have probabilities attached to them. They're more like the columns in the acts by states matrix are not states of nature, but they're attributes like the price, the reliability, the amount of RAM in a computer, right? Whatever the attributes of what the object that you're buying would be. And so there, both models could work and potentially make competing predictions in the setting where, like, you have to pick a setting where they both apply. And you can it is possible to think about a utility function that's defined based on the distance between ideal and the current object. So it's a different kind of utility. It's not the same utility, but now it's like apples to apples, and you can start comparing the two approaches in terms of how well they predict and what intuitions you get. Right? Could you come up with a new domain where now you could make new predictions to go out and test?
Gotcha. I also had one more question. Sorry if I'm taking over. So by using generative AI, you mean you're solving the regression problem with machine learning, right? The multi-dimensional regression problem.
It is, but I mean, there's a sense in which a lot of current generative AI are regressions on steroids, right? It's kind of a neural networks as a function approximator.
Well, yeah, but I honestly kind of think about the generative AI as a sort of a buzzword, mostly related to LLMs, right?
Oh yeah, no, this is not LLMs, but yeah.
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 That was what I was asking.
Okay.
So you're doing like this like machine learning regression sort of thing.
Yeah, so there's different types of regressions. So when I had to go from shoe properties to the cube, I did one type of regression.
Mm-hmm.
When I went from the runner characteristics, like the center of mass oscillation, it was a different type of regression models.
Mm-hmm.
So I had to use different. The details were different, but there are mappings in the regression sense. But the whole point is to be able to create new options that don't exist. So I am generating some, like a new running shoe. I'm able to give the bill of materials to someone to be able to manufacture a new shoe based on the specifics, the specifications.
Oh, I see. Okay, thank you.
Yeah.
I was just wondering if you were familiar with Philip Tetlock's research on human decision-making.
Yes.
And how he is looking at humans and characteristics related to being calibrated to basically to reality and the ability to predict things in the future. And he was sort of a protege of Kahneman. And I found Kahneman to be very interesting in terms of his research on unconscious processes like recency, bias, and things like that. I think what you're doing is very valuable. But I'm just wondering if you also are aware of that, and do you think at some point will there be some way to blend those two types of research, or maybe you could use AI to do that?
We could use AI, right? So I'll if I can pick and choose which part of your question. So the part where the more unconscious and, the more gut level, the thinking fast part. And someone could say, well, what I talked about was more the thinking slow part. How do you represent the problem and thinking about the probabilities, right? And all of that. Even to some extent, the Goldilocks is a type of slow, right? It's algorithmic. You're making evaluations. And the one thing I'll talk about this is that the idea of the fast and slow, or two systems, the unconscious, conscious, right? All that came about when Kahneman was writing his book, the 2011, I think 2011-ish book. So I have a great email exchange with him because he sent me a draft of the book. And in none of the work Kahneman and Tversky published was there any mention of two systems, or fast and slow, or conscious, unconscious. It was nowhere near what they were talking about. And so it's not that, I'm not saying it's wrong or right, I'm just saying it was really something that was added later. It was not part of what they were testing. What they were testing was something, as a different analogy. It's the analogy of optical illusions. And so we use optical illusions to understand how the visual system works. So, right, if we think this is the way the visual system works, then we should be able to present it a scene that we can predict it's going to make a mistake. It's going to see something that isn't there, like train tracks in the distance seem to converge. We know they don't, right? We know that they're parallel, they don't converge, but our eyes sees them converge. So that's an optical illusion. We wouldn't say the visual system is irrational because it has that, because it probably was a very good adaptive cue to use in the environment, that you can infer distance by converging parallel lines as you look out. So the metaphor that they were using was closer to the visual or optical illusions work, which is to learn. They were making predictions about people make judgments and decisions based on some intuitions, like their heuristics work. And it wasn't that the heuristics were fast or slow or conscious or unconscious. It was basically because sometimes the heuristics actually involve more cognitive work than doing the other thing that could have been done. And so anyway, so Kahneman and I went back and forth quite a bit on that. He landed on sticking with the fast and slow because that was a very good way for people to get the intuition of what was happening. But it's not in any of their original work.
Tetlock talks a lot about the inside view versus the outside view of evaluating things, in terms of the outside view might be data, like 10 out of 20 people would get divorced, and the inside view would be, Jack and Jill are getting married. What is their chances of getting divorced? I know them, and so therefore, this is what I think. And so he does a lot of that, comparing the inside and outside view, and he's doing a lot of research on human beings and what attributes of human beings help them be more calibrated to actual events and to what's happening, and how well they can predict what will happen in the future. I'm real familiar with that because I was part of the ACE tournament. So.
Okay, good.
We have time for one more question or so. Anyone else?
Thank you. Really interesting talk. When I do field work and ask people, what would you prefer, or overall, what would you prefer? One really interesting and really troublesome answer I get is, well, that depends. That is, sometimes the decision or the idea is not only shaped by, the dimensions we can get with the individual, but also the dimension of the situation when they make that decision. Ideally, we interview the people exactly in the same situation when they're making that kind of decision, but it's kind of a luxury. So I'm just wondering, is it possible to, I don't know, even add further dimensions, flexibility into the already very flexible generative DM to kind of predict how that ideal point may shift given certain characteristics of the situations? For instance, if instead of just running on a treadmill, can I also predict, how people would like their running shoes when they're running in hills, when they're running in the different settings?
Right.
That's the
Asphalt
question.
versus a trail.
Yes. So I just feel like, because when I'm in the field, I ask people question, there's less of a perceived consistency of preferences. So I feel like that there is a need to, in a certain degree, model what's in the situation. So that's just the question.
Yeah, no, absolutely. I agree with you 100% on that. I'd love to be able to tackle that problem head on and kind of understand how context influences. We're like the vacuum, right? We assume it away. We create kind of very scripted stimuli in our studies, but that, yeah, we need to understand the context. Absolutely.
Well, again, please join me in thanking our guest speaker for the evening. We greatly appreciate a very lively conversation. And on behalf of the Ann Arbor District Library, we thank you for coming.